The most beautiful planet in the solar system may also be one of the most extreme. Beneath Saturn's appearance lies an environment shaped by extreme winds, intense radiation belts, and storms that can span the entire planet. Some of its features are far more extreme than they appear from afar. Why astronomers call Saturn the scariest planet, disturbing scientific reality. When Saturn was first pointed at through a telescope in 1610, it did not look like a planet that made sense. Galileo saw something strange on both sides of it, like small objects stuck to it, and he could not explain it with the tools and knowledge of that time. He thought he might be seeing three separate bodies moving together, and even when he looked again later, the shapes had changed. That early confusion was not a mistake in observation. It was the first sign that Saturn was not going to behave like anything known in the night sky. It was only later, decades after Galileo, that Christian Huygens looked at Saturn with a better telescope and realized that what people were seeing was not objects beside the planet, but a flat, wide system of rings surrounding it. Even then, the idea felt unstable because nothing in nature had prepared astronomers for a planet that looked like it was wearing a structure that large and that precise. As telescopes improved, Saturn slowly became less of a blur and more of a system with detail that kept surprising observers. What started as a simple, bright object in the sky began to show bands across its surface, changes in brightness, and a structure around it that did not behave like a solid body. Even before spacecraft reached it, astronomers could already see that Saturn was not just a larger version of Jupiter or Earth, because its appearance kept shifting depending on viewing angle and time. The rings would sometimes appear thin and sharp, and at other times almost disappear from view, not because they were gone, but because their angle relative to Earth changed. That simple fact already made Saturn feel unstable in a way no other planet did, because its most visible feature was not fixed in place, but constantly changing from our perspective on Earth. When the first spacecraft finally moved towards Saturn, the expectations were still based on limited data from telescopes. But what the probes found changed the entire picture. Pioneer 11 was the first to pass close enough to measure Saturn's environment directly. And what it detected was not just a calm gas giant, but a region filled with strong radiation and a magnetic field that was far more complex than expected. The radiation levels were high enough to raise immediate concern for any future mission planning, and the magnetic field did not line up neatly like Earth's, but appeared tilted and distorted in a way that suggested deep internal motion that was not yet understood. This was the first time Saturn was not just seen, but felt as an environment, and the data showed that it was far more extreme than its soft appearance through telescopes had suggested. When Voyager 1 and Voyager 2 arrived later, the scale of Saturn's system became difficult to ignore. The ring structure was no longer a simple set of bright bands, but a dense and layered system filled with gaps, waves, and fine divisions that behaved almost like a moving disk rather than a static object. Some regions of the rings were so thin they were almost invisible, while others were packed with particles that reflected sunlight strongly enough to dominate the view. The spacecraft also revealed that Saturn was not isolated in space, but surrounded by a large family of moons, each one affecting the system in subtle but constant ways. Gravity was not acting in a simple one-body system here, it was acting across a crowded environment where every object influenced the motion of others, creating patterns that could shift over time. As Voyager data came back, Saturn's atmosphere also began to show details that were not visible from Earth. The planet is made mostly of hydrogen and helium, but that simple description hides the violence inside it. Winds in the upper atmosphere move at speeds that can exceed 1,800 kilometers per hour, far beyond anything seen on Earth, and these winds form long bands that circle the planet in opposite directions at different latitudes. These bands are not just surface patterns, they are part of a deep atmospheric system driven by internal heat that rises from below, meaning Saturn is not just reacting to sunlight, but generating its own energy-driven weather from within. That internal heat is one of the first major mysteries, because Saturn gives off more energy than it receives from the Sun, and the reason for this imbalance is still not fully settled, though it is linked to slow gravitational compression and helium behaviour inside the planet. At the North Pole, Voyager and later Cassini images revealed a structure that looked almost artificial at first glance, a massive hexagon-shaped storm system that remained stable over decades. This hexagon is not a surface feature, but a jet stream locked into a rotating pattern, and its edges are sharp enough that it looks carved, even though it is entirely made of moving gas. Scientists have observed it for years, but the exact reason why a flowing atmosphere settles into a six-sided pattern instead of a circular one is still not fully resolved. Inside that region, storms rotate and interact, but the outer boundary of the hexagon remains intact, holding its shape through continuous motion that should, by simple fluid dynamics, normally break down. Deeper in Saturn's atmosphere, lightning storms appear on a scale that makes Earth weather look small. These storms are not short local events. They can stretch across vast regions and release electrical energy strong enough to be detected from space. Some of them appear and fade over long periods, while others develop into large rotating systems that can last for months. What makes them more unusual is that they occur in an environment where cloud layers are made of ammonia and water compounds mixed under extreme pressure, meaning the chemistry of storm formation is not directly comparable to anything on Earth. The storms are driven by heat rising from below and by rapid atmospheric motion above, creating a system where convection behaves in ways that are still being modelled. Below all of this atmospheric activity, Saturn's magnetic field adds another layer of complexity. Unlike Earth's relatively aligned magnetic field, Saturn's field appears almost perfectly aligned with its rotation axis, which is unusual for a planet with a fluid interior. This alignment suggests internal processes that are still not fully understood, possibly involving metallic hydrogen layers deep inside the planet, where pressure is high enough to change the behavior of hydrogen itself. Around the planet, this magnetic field traps charged particles and forms radiation belts that can affect anything entering the system, including spacecraft, which must be carefully shielded and routed to avoid the strongest regions. The ring system itself is not just visually striking, it is also dynamically unstable in ways that are still being studied. The rings are made of countless particles, mostly water ice, ranging from dust-sized grains to objects as large as small mountains, all orbiting Saturn at different speeds, depending on distance. These particles constantly interact through gravity and collision, creating waves and gaps that shift over time. Some of these gaps are maintained by small moons, known as shepherd moons, which orbit within or near the rings and use their gravity to keep ring edges sharp. Without these moons, the rings would slowly spread out and lose structure, which suggests that the system is not permanent on cosmic timescales. Recent data from the Cassini mission revealed something even more unsettling about the rings, which is that they are slowly disappearing. Material from the rings is being pulled into Saturn through a process often described as ring rain, where charged particles are guided along magnetic field lines and fall into the planet's atmosphere. This means the rings are not just stable structures floating in space, but temporary features that are actively being drained over time. Alongside this, constant bombardment by micrometeoroids from deep space is breaking down ring particles, slowly grinding them into smaller dust that behaves differently in Saturn's environment. Beyond the rings, the moons of Saturn form a system that is just as active and complex as the planet itself. Titan, the largest moon, has a thick atmosphere that is denser than Earth's and contains nitrogen and methane, creating a surface environment with lakes and rivers made of liquid hydrocarbons. The surface is hidden under thick haze, making direct observation difficult, but radar mapping has shown landscapes shaped by liquid flow, even though the liquids are not water. Enceladus, another major moon, has become one of the most important discoveries in planetary science because it ejects plumes of water vapour from cracks near its south pole, suggesting a subsurface ocean beneath its icy crust. These plumes contain organic compounds, meaning there is active chemistry occurring in a hidden ocean far from sunlight. Other moons add more unusual behaviour to the system. Iapetus shows a striking difference between one side and the other, with one hemisphere much darker than the other, a feature linked to material transfer and thermal effects that change surface properties over time. Hyperion, with its irregular shape and chaotic rotation, moves through space in a way that does not settle into a stable spin, instead tumbling unpredictably due to weak gravitational control from its shape and environment. Each of these moons is part of a larger gravitational system where orbits are not fixed in simple paths, but influenced by multiple interacting forces that can shift over time. When all of these elements are considered together, Saturn's system is not a calm region of space, but a place where gravity, radiation, atmospheric motion, and particle physics all interact at once on a massive scale. The planet itself is not solid, the rings are not permanent, the atmosphere is not stable in the way Earth's is, and the moons are not isolated objects, but active participants in a shared gravitational environment. Nothing about it remains static for long periods when measured in astronomical terms, and every layer of the system appears to be in motion, even when it looks still from a distance. This is the reason astronomers describe Saturn in strong terms, not because of fear in a human sense, but because of how many extreme physical systems are packed into one region, and how little of it behaves in a simple or stable way. It is a planet where every observation reveals another layer of motion, another interaction, another system inside a system, all operating at scales and speeds that challenge direct intuition. And that constant complexity is what keeps Saturn one of the most closely studied and least fully understood planets in the solar system. Saturn in pre-space age astronomy. Before any spacecraft ever reached Saturn, everything humans knew about it came through glass lenses on Earth, and that alone shaped how strange the planet felt long before we had real data from space. Early astronomers were dealing with a point of light that was bright enough to stand out in the night sky, yet unstable in appearance once magnified, because even small telescopes from the 1600s were just powerful enough to show that Saturn was not a simple round object like the Moon or Mars. When Galileo first turned his telescope toward it, the image was unclear and limited. But even in that weak view, Saturn did something no other planet did at the time. It seemed to change shape, and that change created confusion that lasted for decades, because there was no known physical explanation for what he was seeing. As telescope design slowly improved across the 17th and 18th centuries, astronomers began to notice that Saturn had a structure around it that did not behave like anything solid, and this structure appeared and disappeared depending on viewing angle. The early idea of handles on the planet came from the fact that the rings were not resolved as continuous bands at first, but as two bright extensions on either side of the planet, almost like ears or arms attached to it. This was not a mistake in observation, it was a limitation of resolution, because the ring system is thin compared to the planet's size and distance, so early instruments blurred it into shapes that the human eye tried to interpret in familiar forms. What made this even more confusing was that over time, those extensions seemed to shrink and even vanish completely when the rings were seen edge-on from Earth, and then slowly return again, which created the impression that Saturn itself was changing shape over years, rather than just being observed from different angles. When Christian Huygens proposed that Saturn was surrounded by a flat ring system, it was a major shift in thinking. But even after that idea was accepted, astronomers still had no clear understanding of what the ring actually was made of, or how stable it might be. Through better telescopes in the late 1600s and early 1700s, the rings began to look less like a single structure and more like layered regions with differences in brightness. But these differences were subtle and inconsistent, often affected by atmospheric distortion on Earth. Observers reported variations in ring thickness, brightness gaps, and uneven shading. But because each telescope had different resolution and each night's atmosphere changed the view, there was no way to confirm if these were real structures or optical effects. This uncertainty kept Saturn in a strange category in astronomy, because it was clearly not simple, but also not fully readable with the tools available at the time. As telescope quality improved further in the 19th century, Saturn began to reveal more consistent patterns. And this is where the idea of structure inside the rings started to form more seriously. Astronomers like Giovanni Cassini observed a dark division in the rings, now known as the Cassini division. And this was one of the first strong pieces of evidence that the ring system was not a single solid sheet, but made of separate parts with gaps between them. This discovery changed the way Saturn was studied, because it suggested that the rings might be composed of many small objects instead of one continuous body. And that idea was not fully accepted at first because it challenged the assumption that celestial structures should behave like solid or fluid surfaces. The Cassini division itself was not just a visual break. It implied that something was actively maintaining that gap, because if the rings were just a passive disk, gravity alone would have caused them to spread and fill in those spaces over time. As observational tools improved, astronomers also began noticing that Saturn's atmosphere had faint banding, similar in concept to Jupiter, but less sharp and harder to track from Earth. These bands were not clearly defined in early telescopes, but under steady viewing conditions, differences in brightness across the planet's surface could be detected, suggesting that Saturn had large-scale atmospheric motion, even though it looked smooth at first glance. These subtle patterns hinted at deep circulation systems beneath the visible clouds. But without spacecraft data, there was no way to measure wind speeds or composition directly. Even so, repeated observations over time showed that Saturn was not a static sphere, but a rotating system with visible atmospheric flow that changed slowly and sometimes unpredictably, depending on seasonal position and viewing angle. One of the most important challenges in pre-space age Saturn observation was the way Earth's atmosphere distorted everything seen through telescopes. Even the best observatories of the 1800s and early 1900s had to deal with turbulence in the air, which blurred fine details and created false structures that could not be confirmed. This meant that astronomers often had to rely on repeated drawings and comparisons over long periods, trying to separate real planetary features from optical noise. Because of this, early maps of Saturn often showed inconsistent ring shapes, uneven shading, and atmospheric details that varied between observers, not because Saturn itself was changing rapidly, but because the signal coming from the planet was being constantly reshaped before it reached the eye. This limitation kept Saturn partly hidden, even as telescopes became stronger. By the early 20th century, photography began to replace hand-drawn observations, and this changed Saturn's studies in a major way because it removed some of the human interpretation from the data. Long exposure images started to reveal clearer ring divisions and more stable atmospheric banding, and over time, astronomers could confirm that structures like the Cassini division were real and not observational artifacts. However, even with photography, the resolution was still limited by Earth's atmosphere, so fine ring structures and small moons remained invisible. What could be seen, though, was enough to confirm that Saturn was a system of multiple interacting parts, not just a planet with a single ring. And this pushed astronomy closer to the idea that Saturn might be a complex gravitational environment, rather than a simple celestial object. As the 20th century progressed, radio astronomy and improved optics allowed scientists to begin estimating Saturn's atmospheric composition, which was found to be mostly hydrogen and helium. But this still did not explain the planet's internal behavior or the source of its atmospheric motion. The banded structure continued to be observed, and seasonal changes in brightness suggested that deeper processes were driving weather patterns far below the visible cloud tops. At the same time, studies of the rings suggested variations in density and particle distribution. But without direct sampling, everything remained indirect inference based on light reflection and orbital mechanics. By the time the space age was approaching, Saturn had already built a reputation among astronomers as a planet that resisted simple explanation, because every improvement in observation revealed new layers instead of closing questions. The rings were not just a feature, but a system with divisions, gaps, and changing brightness. The atmosphere was not smooth, but showed slow-moving patterns that hinted at deep internal energy. Even the tilt and appearance of the rings changed over time in ways that depended on both Saturn's orbit and Earth's position, creating a constant shift in how the planet was seen from Earth. This meant that pre-space age astronomy never saw Saturn in a single fixed state, but always in a changing combination of angle, light, and resolution, which made it feel like a moving target even before any spacecraft confirmed how complex it really was. What made all of this more striking in hindsight is that many of the strange features later confirmed by spacecraft were already hinted at in these early observations, just without the clarity needed to understand them fully. The gaps in the rings, the banded atmosphere, the changing brightness, and the shifting ring angle were all visible in some form from Earth, but they could not be connected into a single physical model until direct exploration began. Pre-space age astronomy did not fail to see Saturn, it simply saw it through layers of limitation that blurred the system into fragments. And those fragments were the first signs that Saturn was not just unusual, but structurally different from most other planets in ways that would only become fully clear much later. The first close encounter, Pioneer 11. Before any spacecraft ever got close enough to Saturn to measure it directly, the planet existed mostly as a distant object of light and structure seen through Earth's atmosphere. But that changed when Pioneer 11 moved into the outer solar system and became the first human-made object to fly past Saturn at close range in 1979, because this was the moment when Saturn stopped being only an image and became a physical environment with measurable forces acting on a spacecraft in real time. And what it revealed was not a calm or simple gas giant, but a system that pushed back with radiation, magnetic pressure, and particle activity that had never been fully expected from earlier models built on telescopic data. As Pioneer 11 approached Saturn, the first major shift in understanding came from the way the planet's radiation environment behaved, because instruments began detecting levels of energetic particles far higher than predicted, forming zones around Saturn where charged particles were trapped and moving at high speed within the planet's magnetic field. And what made this disturbing in a scientific sense was not just the intensity, but the structure of these radiation belts, which were not evenly spread or stable, but shaped into regions that changed with distance and angle, meaning that any spacecraft entering this area would not just face a uniform field, but a layered system of radiation that varied sharply depending on its path. And this immediately changed how Saturn had to be approached in future missions, because it showed that the space around the planet was not empty or safe, but active and potentially damaging to electronics and sensors. At the same time, Pioneer 11 began measuring Saturn's magnetic field more closely, and what the data showed was that the field was far stronger and more complex than expected for a planet of Saturn's composition, especially when compared to earlier assumptions based on Jupiter and Earth, because instead of behaving like a simple dipole aligned neatly with the planet's rotation, Saturn's magnetic field appeared unusually smooth and closely aligned with its axis, yet still strong enough to extend far into space and interact with the solar wind in a way that created a large magnetosphere around the planet. And this combination of strong field strength and unusual alignment raised immediate questions about what was happening deep inside Saturn, since magnetic fields of this type are normally generated by moving conductive material in a planet's interior, meaning that something deep below the visible cloud layers had to be moving in a way that was not yet understood, possibly involving metallic hydrogen under extreme pressure, though at that stage this was still a developing idea rather than a confirmed structure. As Pioneer 11 continued its flyby, it also passed through the region of Saturn's rings, and this was one of the most delicate parts of the mission because there was real uncertainty about whether even small particles in the rings could pose a threat to the spacecraft. And although no major damage occurred, the data returned confirmed that the rings were not empty space, but a dense field of particles spread across a wide region with particle sizes ranging from dust grains to larger chunks, all moving in separate orbits around Saturn. And what stood out in the measurements was how uneven this distribution was, because some areas of the rings contained dense clusters of material, while others were comparatively thin, suggesting that the ring system was actively shaped by gravitational forces rather than being a leftover static structure from the planet's formation. The spacecraft also provided early confirmation that the ring system was interacting with nearby moons in ways that had not been fully visible from Earth, because gravitational influences from small satellites appeared to be shaping gaps and edges within the rings, creating boundaries that were not random but maintained over time. And this was a major shift in thinking because it suggested that the ring system was not simply spreading out evenly under gravity, but was being actively structured by external forces that kept certain regions clear while allowing others to remain dense, meaning that Saturn's rings were part of a dynamic system rather than a passive disk. And this dynamic behavior was one of the first clear signs that Saturn's environment was not stable in the way earlier models had assumed. Another major discovery from Pioneer 11 was the way Saturn's environment affected the spacecraft itself during closest approach, because as it moved through different regions of the magnetosphere, the instruments recorded sudden changes in particle intensity and magnetic pressure, showing that the boundary between Saturn's magnetic field and surrounding space was not smooth, but shifted and responded to solar wind conditions. And this meant that Saturn's space environment was not fixed, but constantly changing as external forces interacted with its internal magnetic structure, creating a region around the planet where conditions could vary over relatively short timescales in space terms. And this variability added another layer of complexity to understanding Saturn as not just a planet, but as a system interacting continuously with the broader solar system. The flyby also helped refine understanding of Saturn's mass and gravitational field, because tracking the spacecraft's trajectory as it curved around the planet allowed scientists to measure small changes in speed and direction caused by Saturn's gravity. And this data helped confirm that the planet's mass distribution was not perfectly uniform, which again pointed back to internal structure and density variations that could not be directly observed but had to be inferred from how the spacecraft moved through space. And this method of indirect measurement became one of the key tools for understanding giant planets, since no direct sampling of their interiors was possible. What made Pioneer 11's encounter especially important was not just the individual discoveries, but the way it changed the overall model of Saturn from a distant visual object into an active physical system filled with radiation, magnetic forces, particle interactions, and gravitational complexity. Because before this mission, Saturn was largely understood through reflected light and orbital motion. But after Pioneer 11, it became clear that the space around Saturn was filled with invisible structure that could affect anything entering it. And this included high-energy particles trapped in magnetic fields, shifting boundaries between solar wind and planetary influence. and ring systems made of countless moving pieces that were constantly interacting with each other and with nearby moons. Even though Pioneer 11's instruments were limited compared to later missions, the data it returned was enough to reshape mission planning for everything that followed, because it showed that any future spacecraft would need to be carefully designed to survive radiation exposure and navigate through regions where particle density could change quickly. And this realization directly influenced the design of later missions like Voyager and Cassini, which were built with much more robust shielding and more precise trajectory planning to avoid the most dangerous zones while still collecting detailed data from safe distances. Voyager flybys, the planet becomes real. When Voyager 1 and Voyager 2 reached Saturn in the early 1980s, the planet stopped being something that could be understood through gradual improvement of Earth-based telescopes and turned into a fully revealed system where every new image and every new data stream added another layer of complexity that no one had fully prepared for. Because up until that point, Saturn had still been partly shaped by guesswork, blurred light, and limited resolution. But Voyager changed that completely by moving directly into the Saturn system and sending back close-range images that showed not just a planet with rings, but a massive and active environment where storms, moons, and ring particles were all interacting in real time. And this shift in understanding was not gradual. It was immediate, because within the first set of images, the rings were no longer a smooth structure seen from far away, but a dense and highly detailed system filled with sharp divisions, thin gaps, bright arcs, and dark lanes that looked almost like tracks carved into a moving disk of material. And what made this more striking was that none of these features were static, because even over the short timescale of Voyager's approach, changes in lighting and angle revealed new structures that had never been seen before from Earth. As Voyager 1 moved closer, the ring system of Saturn became the first major shock in the data, because what telescopes had shown as a few broad bands was actually a highly structured collection of thousands of ringlets, each one separated by narrow gaps that were maintained by gravitational interactions that were not visible directly, but could be inferred from how the particles moved. And these ringlets were not uniform in thickness or brightness, but varied in density and reflectivity depending on particle size and composition, which suggested that the rings were not a single formation, but a constantly shifting system where collisions, gravitational pulls, and orbital resonances were continuously reshaping the structure. And this meant that the rings were not stable in the long-term sense, but were instead part of an active process that depended on both Saturn's gravity and the influence of nearby moons that acted like unseen sculptors, clearing paths and shaping edges by pulling and pushing particles into organized patterns. At the same time, Voyager began revealing details about Saturn's atmosphere that could never be resolved from Earth, because instead of a smooth gas surface, the planet showed strong banded structures with alternating light and dark zones that wrapped around the entire planet. And these bands were not just visual patterns, but indicators of deep atmospheric circulation, where gases were moving at extreme speeds in opposite directions at different latitudes, creating jet streams that encircled the planet and reached wind speeds far beyond anything recorded on Earth. And what made this more complex was that these atmospheric bands were not fixed in place, because they changed in brightness and shape over time, suggesting that internal heat from Saturn was driving weather systems that extended far deeper than the visible cloud layer, meaning that what Voyager was seeing on the surface was only the top layer of a much larger and more active system underneath. As the spacecraft continued its flyby, Voyager 1 also captured detailed images of Saturn's moons, and this was another moment where the system became far more complex than expected, because instead of a few large inactive bodies orbiting a planet, Saturn was surrounded by a wide collection of moons of different sizes and shapes, each one interacting with the rings and with each other through gravitational influence. And some of these moons were large enough to have their own atmospheres or surface features, while others were small and irregular, moving in orbits that appeared stable but were actually influenced by constant gravitational nudges from nearby bodies, creating a system where nothing moved in complete isolation, and every orbit was part of a larger network of interactions that shaped the entire environment over time. One of the most important discoveries from Voyager was the way it showed that Saturn's ring system and its moons were not separate features, but parts of a connected system where gravity acted as a shared force shaping both regions at the same time, because small moons embedded in or near the rings were found to be directly responsible for maintaining gaps and sharp edges within the ring structure, acting as gravitational barriers that prevented particles from spreading evenly. And this explained why some parts of the rings remained sharply defined instead of dissolving into a uniform disk. And it also showed that the system was not static, because these moons were constantly moving and adjusting the structure of the rings as they orbited Saturn, meaning that the ring system was being actively maintained by physical processes rather than existing as a leftover remnant of planetary formation. As Voyager 2 followed a different trajectory, it added more detail to this picture by showing variations in Saturn's atmospheric storms, and by confirming that large-scale weather systems could persist for long periods, including massive storm structures that appeared and evolved over time. And these storms were not isolated events, but part of a global atmospheric pattern driven by internal energy flow, where heat rising from deep inside the planet created convection currents that interacted with rapid rotation, producing banded winds and large storm systems that could span vast regions of the planet. And what made this even more interesting was that some of these storms appeared to interact with each other, merging or changing shape as they moved across different atmospheric bands, suggesting that Saturn's weather was not just layered, but interconnected in a way that allowed energy and motion to transfer across different regions of the atmosphere. The Voyagers also provided important data about Saturn's magnetic field, which showed that the planet was surrounded by a large magnetosphere that extended far into space and interacted strongly with charged particles from the solar wind. And this magnetic field was not just a passive shield, but an active region where particles were trapped, accelerated, and guided along magnetic lines, creating radiation zones that could vary in intensity depending on solar activity and position within the system. And this meant that the space around Saturn was not empty, but filled with invisible structures of energy and particles that shaped how both natural bodies and spacecraft would behave as they moved through it. Another major insight came from the way Voyager data showed how Saturn's ring particles behaved at a small scale, because instead of moving like a continuous fluid or solid disk, the rings were made up of countless individual objects, each following its own orbit, but constantly interacting through collisions and gravitational nudges. And these interactions created wave patterns within the rings that looked like ripples spreading through a surface, but were actually the result of orbital resonances and density variations. And this meant that the rings were not only structured on a large scale with gaps and divisions, but also on a microscopic level, where individual particle behavior contributed to the overall shape and stability of the system. As more data came in, Voyager's observations also highlighted the way light reflected off the rings changed depending on viewing angle and particle composition, which helped scientists understand that the rings were mostly made of water ice with traces of rocky material. And this composition explained their high reflectivity. But it also raised new questions about how such a large system of ice particles could remain in orbit without quickly collapsing or spreading out. And the answer seemed to lie in the constant balance between gravitational forces from Saturn and the influence of nearby moons, which worked together to maintain structure while still allowing slow changes over time. By the time Voyager 1 completed its flyby and Voyager 2 prepared its own encounter, Saturn had already transformed from a distant planet with rings into a full system of interacting physical processes, where atmosphere, rings, moons, radiation, and magnetic fields were all linked together in a way that created constant motion and change. And this realization did not come from a single discovery, but from the accumulation of detailed observations that showed how every part of the system influenced another part, so that no feature could be understood alone without considering the entire environment around it. And this is what made the Voyager missions so important, because they did not just show what Saturn looked like, they revealed how it worked as a connected system where nothing stayed simple once seen up close. Cassini-Huygens mission begins. When the Cassini-Huygens mission was launched towards Saturn, it was not just another step in space exploration, it was a full shift in how humanity approached the planet. Because unlike the brief flybys of Voyager that passed through the system in a matter of days, this mission was designed to stay, orbit, and continuously study Saturn and its moons over many years. And that single difference changed everything about what could be learned. Because instead of snapshots taken during a fast pass, scientists would now receive long streams of data that showed how Saturn behaved over time, how storms developed and faded, how ring structures shifted under gravitational pressure, and how moons interacted with their environment in ways that could never be captured in a single moment. And this long-term approach was essential because Saturn is not a static object that can be understood from a single encounter, but a system that changes slowly and continuously, where time itself becomes part of the data. The design of Cassini reflected this need for long observation, because the spacecraft was built not just to survive the journey to Saturn, but to operate in one of the most complex and harsh environments in the solar system, where radiation levels, magnetic fields, and particle density all vary depending on position. And engineers had to plan for constant exposure to these conditions while still keeping instruments stable enough to take precise measurements. And this required shielding systems, redundant electronics, and carefully planned orbital paths that would allow Cassini to pass through safer regions of Saturn's magnetosphere while still getting close enough to study the rings and moons in detail. And every part of this design was shaped by earlier missions like Pioneer and Voyager, which had already shown that Saturn's environment was far more intense and unpredictable than originally thought, especially in terms of radiation and magnetic structure. When Cassini arrived at Saturn in 2004, the first orbital insertion was a critical moment because it required the spacecraft to slow down enough to be captured by Saturn's gravity. And this maneuver placed it into orbit around a planet that was already known to have strong radiation belts and complex gravitational influences from its moons, meaning that every orbit would need to be carefully controlled to avoid damage while still allowing scientific instruments to gather data from different regions of the system. And once Cassini successfully entered orbit, it immediately began to reveal that Saturn was even more active and structured than previous missions had suggested. Because instead of a simple, layered system of rings and moons, what appeared was a constantly changing environment where ring particles, atmospheric storms, and moon interactions were all happening at the same time, often influencing each other in ways that could be seen only through continuous observation. One of the most important changes Cassini brought was the level of detail in the ring system, because while Voyager had shown that the rings were made of many smaller structures, Cassini revealed that these structures were far more complex than expected, with thousands of narrow ringlets separated by gaps that were maintained by tiny moons and gravitational resonances. And as Cassini orbited Saturn, it was able to watch these structures change over time, showing that the rings were not fixed formations, but living systems of particles constantly being reshaped by gravity and collisions. And this included spiral density waves that moved through the rings like ripples, created by the gravitational pull of moons passing nearby. And these waves allowed scientists to see how energy moved through the ring system, not as a simple flow, but as a series of interactions that constantly reshaped particle distribution. As Cassini continued its mission, it also provided the first long-term view of Saturn's atmosphere, which revealed that storm systems could last much longer than expected and could grow into massive structures that wrapped around the planet, including large storm outbreaks that released enormous amounts of energy and changed the appearance of entire regions of the atmosphere. And these storms were not isolated events, but part of a deeper atmospheric cycle driven by internal heat, where warm gases rise from inside the planet and interact with fast-moving jet streams, creating layers of motion that extend across different latitudes. And what made this more complex was that these layers were not independent, because energy and material could move between them, causing storms to shift position, change shape, or merge into larger systems over time. Cassini also revealed details about Saturn's magnetic field and how it interacts with both the planet and its surroundings. Because as the spacecraft moved through different parts of Saturn's magnetosphere, it recorded changes in particle density and magnetic strength that showed how the field responds to solar wind pressure and internal rotation. And this field was not just a simple protective bubble, but a dynamic region where charged particles were trapped and guided along invisible lines of force, creating radiation zones that varied depending on distance from the planet. And this meant that any object moving through Saturn's space environment would experience constantly changing conditions depending on where it traveled, adding another layer of complexity to mission planning and scientific interpretation. One of the most important parts of the Cassini mission was the way it studied Saturn's moons in close detail, because instead of just being distant objects orbiting the planet, these moons turned out to be active worlds with their own environments and processes. And Cassini's repeated flybys allowed scientists to see how these moons interacted with Saturn's rings and magnetic field, including how some moons helped shape ring edges through gravity, while others showed signs of geological activity driven by internal heat or tidal forces. And this created a system where moons were not separate from the planet, but deeply connected to it through continuous gravitational and physical exchange. Among these moons, some of the most important discoveries came from repeated observations over time, because Cassini was able to return to the same targets multiple times, revealing changes that would have been impossible to detect in a single flyby. And this included variations in surface features, changes in plume activity, and shifts in atmospheric behavior on moons with thick atmospheres. And this long-term monitoring showed that Saturn's system is not just active in space, but active in time, where processes unfold slowly but constantly, making the entire system more like a network of ongoing physical interactions rather than a set of separate objects. Cassini also changed how scientists understood the ring-moon relationship, because it showed that some moons actually exist within or near the rings and directly influence their structure, while at the same time being affected by the same gravitational forces that shape the rings themselves. And this two-way interaction created a feedback system where moons could clear gaps, maintain edges, and even gather material from the rings, while the rings themselves could slowly feed material back into the system, meaning that neither component could be fully understood without the other. And this interdependence was one of the key reasons Saturn's system became known as one of the most dynamically complex environments in the solar system. Saturn's atmosphere, a hydrogen hellscape. Saturn's atmosphere is not a thin layer of gas sitting quietly on top of a planet. It is a deep, layered system built almost entirely from hydrogen and helium, stretched into motion by pressure, heat, and rotation, in a way that creates conditions far beyond anything on Earth. When spacecraft first began measuring it directly, what they found was not a calm outer shell, but a fast-moving environment where gases behave like a fluid ocean that never settles, and where the deeper you go, the more extreme the pressure becomes, until hydrogen itself changes its behavior under crushing weight and high temperature. From a distance, Saturn looks soft and uniform, but inside that soft appearance is a system driven by forces that keep it constantly in motion. And this motion is not small or slow, because the entire upper atmosphere is wrapped in bands of wind that circle the planet at speeds that can exceed 1,800 kilometers per hour, faster than any storm system ever recorded on Earth, and strong enough to stretch around the planet in continuous streams that never fully stop. These winds are not random bursts of air. They are structured jet streams that form clear bands across Saturn's latitude lines, with each band moving in a different direction depending on its position, creating alternating belts of eastward and westward flow that wrap around the planet in long, continuous layers. What makes this system unusual is that these winds are not driven mainly by sunlight like Earth's weather, because Saturn is so far from the Sun that it receives very little energy compared to its own internal heat, meaning that much of what drives its atmospheric motion comes from inside the planet itself, where slow gravitational compression and internal processes release heat that rises upward through the atmosphere, feeding convection that keeps the gas in motion even at high altitudes. This creates a system where heat does not just escape upward in a simple flow, but spreads sideways through jet streams, gets trapped in bands, and circulates across the planet in patterns that can last for long periods without breaking down. As spacecraft like Voyager and Cassini studied Saturn's upper clouds more closely, the banded structure became more detailed and more intense, showing sharp boundaries between zones of rising and falling gas, where lighter regions indicate upward motion and darker regions indicate sinking air. And these zones are not fixed because they shift over time as energy moves through the atmosphere, changing the width and brightness of each band depending on internal activity. This gives Saturn a layered appearance, but the layers are not solid. They are moving streams of gas stacked on top of each other, each one flowing at different speeds and directions. And this difference in speed creates strong shear forces between layers that help generate storms and turbulence across the planet. Deep inside this atmospheric system, pressure rises so quickly that hydrogen gas, which is normally light and simple, begins to behave in unusual ways. And under extreme compression, it transitions into states that can conduct electricity, which is one of the reasons scientists believe Saturn is able to generate a strong magnetic field, even though it is mostly gas on the outside. This internal behavior is not visible directly, but its effects appear in the way the atmosphere moves above it, because the energy coming from below is not steady. It rises in uneven patterns that feed into the jet streams above, giving the entire atmosphere a constant supply of motion that never fully stops. This is why Saturn does not have a quiet weather system, because there is always heat moving upward from deeper layers, constantly feeding the winds and keeping the atmosphere active even when no external changes are happening. One of the most striking features of Saturn's atmosphere is how organized the wind bands remain even at extreme speeds, because instead of breaking apart into chaotic turbulence, the winds form long stable flows that can circle the planet continuously. And this stability comes from the rapid rotation of Saturn itself, which completes a full spin in just over 10 hours, causing strong Coriolis effects that stretch moving gas into horizontal bands, rather than allowing it to move freely in all directions. This rotation locks the atmosphere into a pattern where motion is guided into latitude bands, and once these bands form, they act like channels that direct future flows, keeping the structure in place while still allowing internal changes in speed and strength. Within these bands, storm systems can form that are far larger than anything seen on Earth, including massive rotating systems that can stretch across thousands of kilometers and last for long periods, driven by differences in temperature and pressure between atmospheric layers. Some of these storms appear as bright white outbreaks that rise quickly through cloud layers, while others develop deeper within the atmosphere and only become visible when they reach higher altitudes. And what makes them more complex is that they can interact with surrounding jet streams, sometimes being stretched, slowed, or redirected depending on the surrounding wind structure. This interaction between storms and bands creates a system where no weather event exists in isolation, because every storm is shaped by the larger flow of the atmosphere around it. At higher altitudes, the visible cloud layers of Saturn are made of ammonia ice crystals mixed with other compounds, forming thin cloud decks that reflect sunlight and create the planet's striped appearance. But these clouds are only the top layer of a much deeper system, because below them lie layers where water clouds and ammonia, hydrosulfide clouds, may exist under higher pressure, and below even that is the region where hydrogen becomes dense enough to behave in metallic ways, meaning the atmosphere gradually transitions into a state that blurs the line between gas and liquid as pressure increases. This layered structure is not sharply divided, but changes gradually with depth, creating a continuous transition from visible clouds to deep interior conditions. Lightning activity has also been detected in Saturn's atmosphere, showing that electrical storms occur even in this distant and cold environment. And these lightning events can be extremely powerful, releasing energy in bursts that indicate strong charge separation within storm clouds, likely driven by movement of ice particles and convection within deep cloud layers. These storms are not constant across the planet, but appear in bursts that can last for long periods before fading, suggesting that atmospheric energy builds up in cycles and then releases in large events, similar to, but far larger than thunderstorm systems on Earth. The hexagon storm, a perfect atmospheric anomaly. When Voyager first sent back early hints of Saturn's North Pole, no one expected to see a shape that looked so precise inside a gas planet, because Saturn is not supposed to hold stable geometric patterns in its atmosphere. Yet what appeared at the pole was a massive hexagon-shaped structure sitting directly over the planet's north polar region. And from the first moment it was observed more clearly by later missions, it did not behave like a cloud pattern or a temporary storm system, but like a fixed atmospheric boundary, a jet stream locked into a six-sided shape that wrapped around the pole in a way that should not naturally form in a simple fluid system, especially not one as large and fast-moving as Saturn's atmosphere. What makes this hexagon so unusual is not just its shape, but its scale and stability, because the structure is wide enough to fit multiple Earths across its diameter, yet it remains tightly defined, with each side of the hexagon maintaining a nearly straight boundary as the jet stream flows around the pole at extremely high speeds. And instead of breaking apart into curves or turbulence like most planetary weather systems, it holds its structure for decades, staying almost unchanged from Voyager's first observations in the 1980s to later close-up images from Cassini many years later, which means this is not a short-lived storm or a random atmospheric pattern, but a long-term feature of Saturn's northern atmosphere that has survived for an unusually long time under conditions that should normally destroy such sharp-edge flow structures. As spacecraft like Cassini moved closer and studied the North Pole in higher detail, the hexagon revealed itself not as a cloud formation sitting on the surface, but as a deep jet stream embedded within Saturn's atmosphere, flowing at high speed in a stable path around the pole. And what is important here is that this jet stream is not simply moving in a circle, but forming a polygonal boundary where the flow transitions sharply at certain points, creating straight sections that connect into a six-sided shape. And this is where the real scientific problem begins, because fluid systems like planetary atmospheres usually smooth out over time, especially under constant rotation. Yet Saturn's hexagon does the opposite by maintaining sharp directional changes that remain locked in place for decades without collapsing into a rounded flow. Inside the hexagon, the atmosphere behaves differently compared to the regions outside it, because the central polar area is a rotating mass of gas that sits inside the jet stream boundary, and this inner region can spin at a different rate than the surrounding hexagonal flow, creating a layered structure where one system moves around the pole while another system rotates inside it. And this separation of motion suggests that energy is being organized in a very specific way within Saturn's polar atmosphere, where the jet stream acts like a barrier that holds different rotational zones apart, preventing them from mixing freely. And this separation helps maintain the stability of the hexagon even as the planet continues its rapid rotation. The wind speeds involved in the hexagon are extremely high, consistent with Saturn's general atmospheric behaviour. But what stands out is not the speed itself, but the precision of direction changes along the hexagon edges. Because instead of a smooth curve around the pole, the jet stream makes transitions at nearly fixed points, forming straight segments that connect into a symmetrical shape. And this has led scientists to compare it to patterns seen in controlled fluid experiments, where rotating liquids in laboratory conditions sometimes form polygon-like structures under specific speed and pressure combinations. But even in those controlled environments, such shapes are fragile and temporary, which makes Saturn's long-lasting hexagon even more unusual, because it suggests that some deeper atmospheric or rotational constraint is locking the system into this geometry in a way that is not fully understood. Cassini's extended observations added another layer to this mystery by showing that the hexagon is not just a surface-level cloud pattern, but a deep atmospheric wave system that extends downward into Saturn's cloud layers, meaning that what is visible at the top is only the edge of a much larger rotating structure beneath. And this structure interacts with surrounding winds and storms, while still maintaining its overall shape, which means the hexagon is not isolated, but part of a larger polar circulation system that connects different layers of Saturn's atmosphere through continuous motion and energy transfer. And this connection makes it even harder to explain using simple weather models, because it suggests that Saturn's polar atmosphere is organized in a way that resists normal breakdown into turbulence. Over time, Cassini also recorded changes in lighting, temperature, and cloud movement around the hexagon, showing that while the shape remains stable, the details within it are constantly shifting, with small storms forming along the jet stream edges and moving along the boundary before fading or merging back into the flow. And this creates a system where the overall structure stays fixed while the internal details remain active, almost like a moving framework that guides smaller weather systems along a defined path without losing its overall geometry. And this balance between stability and motion is one of the main reasons the hexagon continues to stand out as one of the most unusual atmospheric features in the solar system. What makes the hexagon even more difficult to explain is the lack of a single clear formation mechanism that can fully account for its shape. Because while jet streams and rotating fluids are well understood in general planetary science, the specific combination of Saturn's rotation speed, atmospheric depth, internal heat flow, and polar conditions produces a situation where multiple forces are interacting at once, and instead of producing chaos, they appear to stabilize into a repeating six-sided pattern that persists over long time periods. And this means that the hexagon is not just a weather event, but a stable flow structure that sits within Saturn's larger atmospheric system, influenced by both deep internal energy and the fast rotation of the planet. Seen in full context, the hexagon is not an isolated curiosity, but part of the same atmospheric system that drives Saturn's extreme winds, banded structure, and deep internal heat flow, because it sits at the pole, where large-scale circulation patterns converge and organize into a stable boundary. And this boundary then shapes how energy and motion move through the upper atmosphere in that region, meaning that the hexagon is both a result of Saturn's atmospheric dynamics and a structure that influences those dynamics at the same time, creating a feedback system that keeps it stable while still allowing constant motion within and around it, lightning and deep storm systems. Saturn's atmosphere is not only fast-moving and layered, it is also electrically active in a way that becomes clear only when spacecraft instruments detect bursts of energy coming from deep inside the cloud systems, because what appears as a smooth, pale planet from a distance hides storm activity that can stretch across areas far larger than entire continents on Earth. And these storms are not shallow surface events. They reach deep into Saturn's cloud layers, where pressure and temperature change rapidly, creating conditions where gas, ice particles and liquid droplets interact in ways that build up electrical charge over time until it is released in sudden flashes of lightning that can be detected even from space. These lightning systems were first confirmed in detail during missions like Voyager and later studied more closely by Cassini, where sensors picked up radio signals known as Saturn electrostatic discharges, which are bursts of energy produced by lightning deep inside the atmosphere. And what made these signals important is not just their presence, but their strength and scale, because they indicated storm systems that were far larger and more energetic than typical thunderstorms on Earth, with individual storm cells spreading over massive regions and producing repeated electrical activity over long periods rather than short isolated strikes, which suggests that Saturn's atmosphere is capable of building and maintaining storm energy on a scale that does not collapse quickly, but instead continues as long as the internal conditions feeding it remain active. Inside these storm systems, the structure is driven by strong vertical motion, where warm gases rise from deeper layers of the atmosphere while cooler gases sink. And this movement creates friction and separation of charged particles within cloud layers made of ammonia, water, and other compounds under high pressure. And as these particles collide and separate, they build up electrical charge in a way similar to Earth's thunderstorms, but on a much larger scale, because the vertical depth of Saturn's storms can extend far deeper into the atmosphere, meaning the charge separation happens over a larger physical space and can therefore store far more energy before releasing it, which is why the resulting lightning bursts are so powerful and widespread. What makes these storms even more unusual is their size, because some of them are not limited to small weather cells, but can expand into massive systems that wrap around large portions of the planet, sometimes forming bands or clusters of storms that appear in specific latitude regions where atmospheric conditions are favourable for convection. And these storm regions can remain active for long periods, fading and reappearing as energy flows shift within the atmosphere, which suggests that Saturn's storm systems are not random events, but part of a larger atmospheric cycle driven by internal heat rising from deep within the planet, constantly feeding energy upward into the cloud layers where it is released in bursts of weather activity. As spacecraft like Cassini observed these storms over time, it became clear that they are not only large, but also deeply embedded in Saturn's atmospheric structure, because they interact with the surrounding jet streams and banded winds, which can stretch, distort, or even redirect storm cells as they move across different atmospheric zones. And this interaction means that storms are not free-floating systems, but are shaped continuously by the strong east-west winds that dominate Saturn's atmosphere. So a storm rising in one region can be pulled apart, reshaped, or intensified depending on how it moves through these fast-moving wind bands, creating a system where storms are constantly being built and broken down by the surrounding flow of gas. Some of the most intense storm activity on Saturn appears as large white outbreaks that suddenly brighten parts of the atmosphere, often signaling rapid upward motion of material from deeper layers. And these outbreaks can spread quickly, covering large areas in a short time before slowly fading as the energy driving them disperses. But during their active phase, they can dominate entire regions of the planet's visible atmosphere, changing how Saturn appears even from distant observation points. And these events are not rare isolated cases, but part of a recurring pattern that shows Saturn's atmosphere is capable of releasing stored energy in sudden, large-scale events that reshape cloud structure over vast distances. Deeper inside these storm systems, the vertical structure becomes more complex, because as material rises and cools, different compounds begin to condense at different altitudes, creating layered cloud decks where ammonia ice forms higher up, while water clouds exist deeper down under higher pressure. And this layering creates multiple zones of instability where rising and falling gases interact. And this interaction helps sustain electrical charge separation over time, allowing storms to maintain lightning activity across long periods instead of producing single short bursts. And this continuous activity suggests that Saturn's storms are powered by a steady flow of internal energy rather than short-lived atmospheric disturbances. What also stands out in Saturn's lightning systems is how deeply they are tied to the planet's overall energy balance, because Saturn emits more energy than it receives from the Sun, and this internal heat rises slowly through the atmosphere, feeding convection currents that drive storm formation, meaning that lightning storms are not just weather events, but part of the planet's way of releasing internal heat into space. And this connection between deep heat flow and atmospheric storm activity creates a direct link between Saturn's interior and its visible weather systems, where changes deep below the cloud tops can eventually appear as electrical storms far above. Saturn's internal heat mystery. Saturn sits far from the Sun, where sunlight is weak and spread out over a huge distance. Yet when spacecraft measured the planet's energy output directly, what they found did not match what should have been possible from sunlight alone, because Saturn is releasing more heat into space than it receives from the Sun, and this means the planet is producing extra energy from inside itself, turning it into a world that is slowly leaking internal heat through its atmosphere. And this is not a small difference. It is large enough to affect weather, wind speeds, storm formation, and even the deep structure of the planet's atmosphere, because that extra heat is what keeps Saturn's upper layers active, fast-moving, and constantly changing instead of settling into a slow, cold, and quiet state. To understand why this is important, it helps to think about what Saturn should be doing if it only relied on sunlight, because at that distance from the Sun, the energy it receives is weak and would normally only heat the uppermost cloud layers slightly, leading to a much calmer atmosphere with less vertical motion, fewer deep storms, and weaker winds. Yet Saturn does the opposite of this expectation, because its winds reach extreme speeds, its atmosphere is highly banded, and its storms are powerful and long-lasting, which means there must be another source of energy feeding the system from below. And when scientists measured the planet's infrared radiation, they confirmed that Saturn is emitting significantly more heat than it absorbs, showing that internal processes are actively releasing energy that was stored or generated within the planet itself. One of the main explanations for this internal heat comes from the slow gravitational compression of Saturn's massive interior, because the planet is made mostly of hydrogen and helium, and under its own gravity, these gases are being slowly compressed over time, and as they are squeezed deeper inside, pressure and temperature increase, causing the planet to release heat gradually as it contracts, which is a process that can continue for billions of years in gas giant planets. But Saturn shows something extra on top of this general process, because its heat output is higher than simple models of gravitational compression alone would predict, which suggests that there is another mechanism working inside the planet that adds to this energy release. A major part of this mystery involves helium inside Saturn's deep interior, where under extreme pressure, helium does not stay evenly mixed with hydrogen, but may begin to separate out and form droplets that sink deeper into the planet. And as these helium droplets fall inward under gravity, they release additional energy in the form of heat, similar to how falling material converts potential energy into thermal energy. And this process, often described as helium rain, would create a slow but continuous release of heat deep inside Saturn, adding to the planet's overall energy output and helping explain why it emits more heat than it receives from the Sun, while also linking directly to internal layering and material separation within the planet's deep interior. This internal heat does not stay trapped inside Saturn, it moves upward through convection, where hot material rises and cooler material sinks, creating large-scale circulation patterns that extend from deep inside the planet up to the visible cloud layers. And this vertical motion is one of the key reasons Saturn's atmosphere is so active, because as heat rises, it drives winds and jet streams that form the banded structure seen across the planet, meaning that the visible atmosphere is directly powered by processes occurring far below. And without this internal heat, Saturn's weather system would be far weaker, less structured, and much less dynamic than what spacecraft have observed. As this heat reaches higher layers, it does not escape evenly, because Saturn's atmosphere is layered in such a way that different gases and cloud systems respond differently to temperature changes. So rising heat can create regions of instability where storms form, while other areas remain relatively stable. And this uneven release of energy helps create the banded appearance of the atmosphere, because some regions are constantly being energized while others are sinking and cooling, creating alternating belts of rising and falling gas that wrap around the planet. And this is directly tied to the planet's fast rotation, which organizes the flow into horizontal bands instead of allowing heat to spread randomly in all directions. The importance of Saturn's internal heat becomes even clearer when it is compared to other giant planets, because while Jupiter also emits more heat than it receives, Saturn's energy balance does not match early predictions based on simple cooling models, meaning that something about Saturn's internal structure or evolution is different enough to produce this level of excess heat. And this difference is one of the reasons scientists study Saturn so closely, because it suggests that gas giant planets do not all evolve in the same way, even when they look similar from a distance. And the internal processes that control their heat flow may depend on subtle differences in composition, pressure, and long-term evolution. This constant release of internal energy also connects directly to Saturn's storms and lightning activity, because as heat rises from deep inside, it drives convection currents that feed storm systems in the upper atmosphere, creating the large-scale electrical storms that have been observed by spacecraft. And without this internal heat source, those storms would not have the energy needed to grow to such massive sizes or persist for long periods, which means that Saturn's visible weather is not just surface activity, but the final stage of a deep energy flow that begins far below the cloud tops and ends in the dramatic storm systems seen from space. The magnetic field, a distorted giant shield. Saturn's magnetic field is not something you can see directly, yet it defines a huge invisible region around the planet that controls how charged particles move, how radiation behaves, and how the space environment around Saturn is shaped. And when spacecraft like Pioneer, Voyager, and Cassini passed through this region, they did not just cross empty space. They entered a structured magnetic system that stretched far beyond the planet itself, forming what scientists call the magnetosphere, a massive bubble carved out of the solar wind by Saturn's internal magnetic activity. And what makes this system unusual is not just its size, but its structure. Because unlike Earth's magnetic field, which is tilted significantly relative to its rotation axis, Saturn's magnetic field is almost perfectly aligned with its rotation, creating a symmetry that should normally make the field simpler. Yet instead of being simple, Saturn's magnetic environment turns out to be one of the most complex particle systems in the outer solar system. The magnetosphere of Saturn is created by the motion of electrically conductive material deep inside the planet, most likely in a layer of metallic hydrogen where pressure is so high that hydrogen behaves like a metal and can carry electric currents. And as Saturn rotates rapidly, completing a full spin in just over 10 hours, this conductive layer moves and generates a magnetic field that extends outward into space, wrapping around the planet and forming a giant protective region that deflects solar wind particles. But this protection is not smooth or uniform, because the field interacts constantly with charged particles from both the Sun and Saturn's own moons, especially Enceladus, which releases water vapor into space adding material that becomes ionized and trapped in the magnetic environment, meaning that Saturn's magnetosphere is not just shaped by the planet itself, but also by external and internal sources of particles that constantly feed into the system. When spacecraft entered this region, one of the first things they detected was that Saturn's magnetic field is strong enough to trap large amounts of high-energy particles, creating radiation belts that extend around the planet in donut-shaped regions where charged particles spiral along magnetic field lines at extremely high speeds. And these particles are not stationary. They move in complex paths guided by the magnetic field, bouncing between polar regions and drifting around the planet, forming layers of radiation that vary depending on distance, energy level, and interaction with Saturn's rings and moons. And this means that any object entering this region is exposed to a constantly changing environment where radiation intensity can increase or decrease depending on position, making the magnetosphere not just a protective shield, but also a hazardous zone filled with energetic activity that must be carefully navigated by spacecraft. What makes Saturn's magnetic field especially unusual is its near-perfect alignment with the planet's rotation axis, because in most planets with active magnetic fields, there is a noticeable tilt between the magnetic axis and the rotational axis. But Saturn's field appears almost perfectly centered, which initially suggested a simpler internal structure. Yet this simplicity is misleading, because despite the alignment, the magnetosphere is highly dynamic, with shifting particle densities, variable radiation belts, and interactions with solar wind that constantly reshape its outer boundaries. Meaning that even though the field looks geometrically simple, the environment it creates is far from stable or uniform. And this contradiction between structural alignment and environmental complexity is one of the key reasons Saturn's magnetic system remains difficult to fully model. Inside this magnetic environment, charged particles behave in ways that create layered regions of activity, because as particles become trapped by the field, they spiral along magnetic lines and accumulate in specific zones, especially near the equatorial region where the rings lie. And this creates an overlap between the ring system and the magnetosphere, meaning that dust and ice particles from the rings can become electrically charged and interact directly with the magnetic field, leading to processes where ring material can be slowly altered, moved, or even drawn into Saturn's upper atmosphere. A process often described as ring rain, where material from the rings falls along magnetic field lines into the planet, linking the ring system and magnetic field into a single interacting environment rather than two separate features. At the same time, the magnetosphere extends far beyond the visible planet and forms a boundary where Saturn's influence meets the solar wind, a stream of charged particles flowing outward from the Sun. And this boundary is not fixed because it shifts depending on solar activity, meaning that the size and shape of Saturn's magnetic bubble can expand or contract over time. And this changing boundary creates regions of turbulence where solar particles collide with Saturn's trapped radiation environment, producing additional energetic interactions that can ripple through the system. And these interactions help explain why Saturn's magnetosphere is not a simple static shield, but a constantly changing region where external space weather and internal planetary motion both play active roles. As spacecraft moved deeper into Saturn's magnetic field, they also recorded how the field influences particle motion in ways that create large-scale structures within the magnetosphere, including current sheets and rotating plasma regions that co-move with Saturn's rotation, forming a system where charged particles are not randomly distributed, but organized into large flowing structures that circle the planet. And this organized motion is driven by the combination of magnetic forces and rapid planetary rotation, which together create a dynamic environment where plasma behaves almost like a fluid trapped within invisible magnetic boundaries, constantly shifting but still following the overall shape of the field. Another important aspect of Saturn's magnetic field is its interaction with the planet's moons, especially those that release gas or water vapor into space. Because once this material becomes ionized, it is captured by the magnetosphere and becomes part of the charged particle environment, adding new layers of complexity to the system. And this means that Saturn's magnetic field is not just shaped by the planet's interior, but also continuously modified by external material entering the system from orbiting bodies, creating a feedback loop where moons influence the magnetosphere and the magnetosphere influences the environment around the moons, leading to a tightly connected system of magnetic and particle interactions that extend across the entire Saturnian system. Over long periods, the interaction between Saturn's rotation, internal conductive layers, and trapped charged particles creates a magnetic environment that is stable in overall shape, but constantly active at smaller scales, where particles move, collide, and change energy states while remaining trapped within the broader field structure. And this combination of large-scale stability and small-scale activity is what makes Saturn's magnetosphere so unusual compared to simpler planetary fields, because it maintains a clear overall structure while supporting continuous energetic motion within it, rather than settling into a quiet equilibrium. Radiation environment, invisible hazard zone. Saturn's radiation environment is one of the most dangerous regions in the entire solar system, not because it is visible or dramatic in the way storms or lightning are, but because it is completely invisible while still carrying enough energy to damage spacecraft systems, interfere with electronics, and slowly degrade instruments over time. And this hidden hazard comes from charged particles trapped inside Saturn's magnetic field, forming radiation belts that surround the planet in thick layers where high-energy particles move at extreme speeds along magnetic field lines, constantly bouncing between northern and southern regions, while spiraling around the planet, creating a dynamic and persistent zone of energetic activity that no spacecraft can pass through without careful planning and protection. These radiation belts are made up of electrons and ions that have been captured by Saturn's magnetosphere, and once trapped, they do not simply stay still, but move in complex paths controlled by magnetic forces, forming regions where particle density and energy levels vary depending on distance from the planet and interaction with Saturn's rings and moons. And what makes this system especially important is that these particles are not evenly distributed, because some regions contain intense concentrations of high-energy electrons that can penetrate spacecraft shielding, while other regions are relatively less active, meaning that the radiation environment changes dramatically depending on the exact path a spacecraft takes through Saturn's space. When compared to Earth, the difference becomes clear in terms of intensity and scale, because Earth also has radiation belts known as the Van Allen belts. But Saturn's belts extend across a much larger system and contain particles that are influenced by a far stronger and more extensive magnetosphere, meaning that the volume of space affected by radiation is significantly larger, and spacecraft entering Saturn's environment must deal with not only stronger particle flux in certain regions, but also a wider spatial distribution of energetic particles that can affect them for long periods as they orbit the planet, rather than brief passes through localized zones. What makes Saturn's radiation environment even more complex is the interaction between these energetic particles and the planet's ring system. Because as charged particles move through space, they can collide with ring material or be absorbed and re-emitted by dust and ice particles, creating changes in particle density and energy distribution that are not static but constantly evolving as the system rotates and as solar activity changes the outer boundaries of the magnetosphere. And this means that the radiation belts are not fixed structures but living regions of space that respond to both internal planetary conditions and external solar influences. Spacecraft like Pioneer, Voyager, and Cassini all had to account for this radiation environment in their design, because exposure to high-energy particles can gradually damage electronic components, disrupt data collection, and cause long-term degradation of sensors, and this is why spacecraft are built with shielding and placed on carefully calculated trajectories that minimize time spent in the most intense regions of radiation, especially near Saturn's inner magnetosphere, where particle density can become particularly high. And even then, mission planners must balance scientific goals with safety constraints. Because some of the most interesting regions of Saturn, including areas near the rings and inner moons, are also among the most hazardous in terms of radiation exposure. The radiation environment also plays a direct role in shaping the behavior of Saturn's atmosphere, because when high-energy particles enter the upper layers of the atmosphere, they can collide with gas molecules and trigger chemical reactions, producing auroras near the polar regions where magnetic field lines converge. And these auroras are not just visual displays, but indicators of energy transfer between the magnetosphere and the atmosphere, showing how charged particles are funneled along magnetic lines and deposited into the upper atmosphere, where they release energy in the form of light and heat, linking the invisible radiation belts directly to visible atmospheric phenomena. Over time, observations have shown that Saturn's radiation intensity is not constant, because it can vary depending on solar activity and internal changes within the magnetosphere, meaning that the hazard level for spacecraft can change during different phases of the planet's interaction with the solar wind. And this variability adds another layer of uncertainty to exploration, because it means that radiation exposure cannot be treated as a fixed condition, but must be continuously monitored and adapted to as conditions evolve, making mission planning more complex and requiring constant adjustments in spacecraft positioning and data collection strategies. Inside the radiation belts, particles move in highly structured ways, following magnetic field lines while also drifting slowly around the planet, creating layered regions where energy is stored and released over time. And this motion is not random, but organized by the shape of Saturn's magnetic field and its rotation, which together create a system where particles are confined but constantly active, producing a persistent energetic environment that surrounds the planet, like an invisible shell of motion and force. The ring system, structure, and scale. Saturn's ring system is one of the most misunderstood structures in the solar system when seen from Earth, because what looks like a solid, thin band wrapped around the planet is actually a wide, layered disk made of countless individual particles, all moving independently at different speeds, all following their own orbits, and all interacting through gravity and collisions in a way that creates the illusion of a continuous structure when viewed from far away, but breaks into a highly detailed and structured system when seen up close by spacecraft like Voyager and Cassini, revealing that the rings are not a single object at all, but a vast collection of ice, dust, and rock fragments spread across a huge region of space. The main ring system is divided into several major sections, labelled A, B, and C rings, with additional faint extensions known as D, E, F, and G rings, and each of these regions has different density, particle size distribution, and brightness, which comes from differences in composition and the way sunlight interacts with the material, because most of the ring particles are made of water ice mixed with smaller amounts of rocky material and dust. And this composition gives the rings their high reflectivity, allowing them to shine strongly in sunlight. But the brightness is not uniform, because denser regions reflect more light, while sparse regions appear darker, creating visible structure even from a distance. The B ring is the most massive and bright part of the system, containing the highest concentration of material and forming the most visually dominant section when the rings are observed from Earth or spacecraft. And within this ring, the density of particles is so high that collisions between ice fragments are frequent, constantly reshaping local structures and maintaining sharp boundaries within the ring system, while the A ring lies just outside it, slightly less dense, but still highly structured, containing multiple gaps and divisions that are maintained by gravitational interactions with small moons embedded within or near the rings, which act as natural sculptors by clearing paths and controlling particle motion through repeated orbital influence. The C ring, in contrast, is much more transparent and less dense, containing smaller particles spread across a wider area, making it appear faint when compared to the brighter B and A rings. But even within this faint region, there is still complex structure, including subtle variations in particle density and wave patterns caused by gravitational interactions with Saturn's moons and internal resonances, showing that even the less visible parts of the ring system are still dynamically active and shaped by the same forces that govern the rest of the system. Beyond these main rings, the D ring lies closest to Saturn and is extremely faint, containing very fine dust particles that are influenced strongly by Saturn's magnetic field and atmospheric drag, making it one of the most delicate and unstable parts of the system, while the E ring is much wider and more diffuse, and is strongly connected to the moon Enceladus, which releases jets of water vapor and ice particles into space, feeding material directly into the E ring and continuously replenishing it, making this ring a direct example of how Saturn's moons actively contribute to the structure of the ring system. Farther out, the F ring stands out as one of the most complex and dynamic regions because it is narrow, bright, and constantly changing shape due to the gravitational influence of small shepherd moons that orbit near it, causing the ring to twist, braid, and form clumps of material that shift over time, creating a structure that appears almost unstable, but is actually maintained by continuous gravitational interaction. And beyond this lies the faint G ring, which is spread out and difficult to observe, containing sparse material that forms a very weak ring structure, again influenced by nearby moons and gravitational resonances that keep the particles loosely organized. One of the most important aspects of the ring system is its scale, because while it appears thin when seen from Earth, the actual width of the ring spans tens of thousands of kilometers, while the thickness in most regions is surprisingly small, often only tens of meters to a few hundred meters in dense regions, which creates a strong visual misperception because the rings look like solid discs in images. But in reality, they are extremely thin compared to their width. And this thinness is maintained by constant collisions and gravitational settling, where particles flatten into a disc-like shape over time due to repeated interactions. Another key point in understanding the rings is that every particle within them orbits Saturn independently, meaning there is no rigid structure holding the rings together, and instead each fragment follows its own orbital path determined by distance from Saturn, with inner particles moving faster and outer particles moving slower, creating a differential motion that constantly reshapes the ring system over time. And this motion is not smooth because collisions between particles create waves, gaps, and density variations that propagate through the rings like ripples, showing that the system is always in a state of controlled change rather than static stability. The composition of the rings plays a major role in how they appear and behave, because water ice dominates most of the system, making the rings highly reflective, but the presence of rocky material and dust affects how light is scattered and how particles interact during collisions. And over time, these collisions grind larger fragments into smaller particles, meaning the rings are slowly evolving as material is broken down and redistributed across different regions, creating a system that is both structured and slowly changing under constant physical processes. One of the most important discoveries from spacecraft observations is that the rings are not permanent on cosmic timescales, because processes like micrometeoroid bombardment, gravitational interactions, and material loss into Saturn's atmosphere through magnetic field interactions all contribute to the gradual erosion of the ring system, meaning that what appears as a stable feature in the sky is actually a temporary structure in astronomical terms, continuously shaped by both creation and loss of material. Ring instability, A temporary structure? Saturn's rings look permanent when seen through a telescope or in spacecraft images, like a fixed feature that has always been there and will always remain. But when scientists started measuring the rings closely using spacecraft data and long-term observations, a very different picture began to form. Because instead of behaving like a stable structure that simply orbits Saturn unchanged, the rings showed signs of slow loss, constant erosion, and material exchange with the planet itself. And this led to the idea that the rings are not permanent at all, but a temporary structure in planetary terms, held together for now by balance, but slowly breaking down over time under multiple physical processes that are always at work. One of the strongest pieces of evidence for this comes from what is now known as ring rain, where charged particles from the rings are pulled along Saturn's magnetic field lines and fall into the planet's upper atmosphere, meaning that material that once belonged to the rings is gradually being removed and absorbed by Saturn itself. And this process is not theoretical. It has been detected through measurements of charged particle flow and atmospheric composition changes, showing that the rings are actively losing mass. And this loss is not a one-time event, but a continuous process that slowly drains material from the ring system over time, turning what looks like a stable disk into a system that is constantly leaking material inward. At the same time, the rings are also being eroded from the outside by micrometeoroid bombardment, where tiny particles from deep space collide with ring material at extremely high speeds, breaking larger ice chunks into smaller fragments and gradually grinding the system down into finer dust. And this dust behaves differently from larger particles, because it is more easily influenced by Saturn's magnetic field and solar radiation pressure, which means it can be pushed out of stable orbits or pulled into the planet more easily, adding another layer of slow but constant loss to the system. And over long timescales, this process changes not just the size of particles in the rings, but the overall brightness and structure of the ring system itself. When scientists model these processes over time, they find that the rings cannot remain unchanged for billions of years without a source of replenishment, because the rate of material loss through ring rain and micrometeoroid erosion suggests that the current ring system would gradually disappear if nothing replaced it. And this leads to a major question about age, because if the rings were as old as the solar system itself, they should already be much darker and more eroded than what we observe today. Yet the rings are still bright and composed mostly of clean water ice, which suggests that they may be relatively young in cosmic terms, possibly formed or refreshed within the last few 100 million years, rather than existing since Saturn itself formed. Another important factor in ring instability comes from gravitational interactions with Saturn's moons, because many small moons orbit near or within the ring system and act as both stabilizers and disruptors, shaping edges and gaps through gravitational forces while also exchanging material with the rings. And in some cases, these interactions can lead to slow loss of ring particles as they are pulled into moons or redistributed into different orbits, meaning that the ring system is not only losing material into Saturn and space, but also constantly being reshaped by its own satellite system, which adds to the idea that the rings are not fixed, but part of an evolving gravitational environment. Spacecraft observations, especially from Cassini, also showed that the rings contain very little contamination compared to what would be expected if they had existed for billions of years, because over long periods, constant exposure to dust from space should darken and chemically alter the icy particles. Yet many regions of Saturn's rings remain relatively bright and clean, which suggests that the material is either being refreshed or is younger than expected. And this observation has pushed scientists toward the idea that a large event may have created or significantly altered the rings in relatively recent geological time, such as the breakup of a moon or a large icy body that was torn apart by Saturn's gravity, creating the ring system we see today. At the same time, the structure of the rings themselves shows signs of ongoing change because density waves, spiral patterns, and gap structures within the rings are not static, but move and evolve over time under the influence of gravitational resonances with moons, meaning that even the internal structure of the rings is constantly shifting. And while these changes happen slowly on human timescales, they become significant when viewed over millions of years, suggesting that the rings are not only losing material, but also continuously reorganizing what remains, creating a system that is always in transition. Another key piece of evidence for ring instability comes from measurements of mass and density distribution, because Cassini data showed that the total mass of the rings is lower than earlier estimates, which means the system may not be as long-lived or as massive as previously assumed. And this lower mass makes it easier for external forces like radiation, micrometeoroid impacts, and gravitational interactions to gradually alter the system over time, pushing it toward a slow decline rather than long-term stability, especially in regions closer to Saturn, where ring rain is strongest and magnetic effects are most active. When all of these processes are combined, the picture that emerges is not of a permanent ring system, but of a structure caught in a slow cycle of creation, erosion, and redistribution, where material is constantly being added in small amounts through collisions and moon activity, but also being removed through atmospheric loss and space erosion. And the balance between these processes determines how long the rings can remain visible in their current form. And current evidence suggests that this balance may not last indefinitely, meaning that the rings we see today are part of a temporary phase in Saturn's long history, rather than a permanent feature of the planet. What makes this even more striking is that the rings appear visually stable on short timescales, giving the impression of permanence when seen from Earth or even from spacecraft over a few years. But beneath that stable appearance is a system that is constantly losing material, constantly being reshaped, and constantly interacting with external forces, meaning that Saturn's rings are not a static structure suspended in space, but an evolving system that is slowly changing shape and mass over time. And this slow transformation is only visible when the data is stretched across long periods, revealing a system that is far more fragile and temporary than its appearance suggests. Ring rain, Saturn, is losing its rings. The discovery of ring rain came from spacecraft measurements that detected unusual streams of charged particles moving from the rings towards Saturn's atmosphere. And this was not expected because the rings were originally thought to be mostly isolated, held in stable orbits by gravity alone. But instruments on missions like Cassini showed that the rings are electrically active environments where dust and ice particles can become charged through sunlight, collisions, and interaction with Saturn's magnetic field. And once these particles gain an electric charge, they no longer behave purely as neutral debris, because they begin to respond strongly to magnetic forces that guide them along invisible field lines extending from the rings down into the planet's atmosphere. This process becomes possible because Saturn has a very strong and large magnetic field that surrounds the planet and connects different regions of space through structured magnetic lines. And these lines act like pathways for charged particles, meaning that once ring material becomes ionized, it does not simply continue orbiting Saturn in a flat disk, but instead can be lifted or pulled along these magnetic channels, slowly spiraling inward toward the planet. And as these particles descend, they collide with gases in Saturn's upper atmosphere, where they are absorbed and create detectable changes in atmospheric composition, confirming that material from the rings is not just orbiting indefinitely, but is actively being transferred into Saturn itself. What makes this even more significant is the scale of the loss, because ring rain is not a rare or isolated event. It is a continuous process that affects large regions of the ring system, especially in areas where the magnetic field is strongest and where ring particles are more easily ionized. And over long periods, this means that Saturn is steadily losing material from its rings, not in a sudden collapse, but in a slow and constant downward flow that drains the system particle by particle. And this slow leakage changes how scientists think about the long-term stability of the rings, because it shows that the rings are not closed systems, but open systems that exchange material with the planet below. The process is also influenced by the structure of Saturn's magnetosphere, because the magnetic field is not uniform. It has regions of varying strength and shape that depend on rotation, solar wind pressure, and internal plasma movement. And these variations create different conditions across the ring system, where some regions are more strongly connected to magnetic field lines than others, meaning that ring rain is not evenly distributed, but concentrated in specific zones where the connection between rings and atmosphere is strongest. And this uneven loss of material contributes to gradual changes in ring structure over time, as some regions thin out faster than others. Inside the rings themselves, constant collisions between particles play a key role in preparing material for this process. Because as ice and dust fragments collide at high speeds within the ring plane, they can generate small charged particles or break off fine dust that is more easily influenced by electromagnetic forces. And once these smaller particles become charged, they are more likely to be captured by magnetic field lines, which increases the rate at which material can be transported away from the rings and into Saturn's atmosphere, meaning that even the internal dynamics of the rings are directly linked to their gradual loss. When spacecraft like Cassini passed through regions near Saturn's inner rings, they directly measured changes in particle density and detected signatures consistent with material falling into the atmosphere, including changes in ion composition and electrical activity that match predictions of ring rain models. And these measurements provided strong evidence that the rings are not just passively orbiting Saturn, but are actively interacting with the planet's atmosphere through magnetic and electrical processes that slowly remove material over time. The effect of ring rain is most visible in Saturn's upper atmosphere, where incoming particles from the rings interact with hydrogen and helium gas, creating chemical changes and localized energy input that would not exist without this external source of material. And this connection between rings and atmosphere shows that the two systems are not separate, but physically linked through magnetic field lines, meaning that what happens in the rings directly affects the planet below, and what happens in the planet's magnetic field directly influences the structure and lifetime of the rings. Over long timescales, this process becomes critical to understanding the future of Saturn's rings, because if ring rain continues at the observed rate without a strong source of replenishment, the rings will gradually lose mass and thin out, especially in the inner regions where magnetic connections are strongest. And this leads to the idea that the rings are not permanent features of Saturn, but temporary structures in a slow cycle of creation and loss, where material is constantly being redistributed between orbit and atmosphere. Micrometeoroid bombardment. Saturn's rings are constantly being hit by a stream of tiny particles coming from deep space, and this process never stops, because even though space looks empty, it is filled with microscopic dust grains, fragments from comets, and leftover debris from early solar system formation. And when these particles enter Saturn's ring system, they strike ring ice at extremely high speeds, often tens of kilometers per second. And at those speeds, even a particle smaller than a grain of sand carries enough energy to break apart larger chunks of ice, chip away surfaces, and slowly grind the rings down over time, turning solid, icy fragments into smaller and smaller pieces that change how the rings behave both physically and visually. This constant bombardment is one of the main reasons the rings are not stable over long timescales, because every impact removes material from the system or reshapes it into finer dust that behaves differently under gravity and electromagnetic forces. And unlike larger ring particles that follow stable orbits around Saturn, these tiny fragments are more easily influenced by solar radiation pressure and Saturn's magnetic field, meaning they can be pushed out of the ring plane or pulled into the planet's atmosphere, adding another slow but continuous pathway for ring loss that works alongside ring rain and gravitational interactions with moons. What makes micrometeoroid bombardment especially important is that it does not require large collisions to have a major effect, because even a steady flow of very small impacts over millions of years can completely change the composition and structure of the rings, gradually darkening ice particles by mixing them with non-icy material and breaking down larger structures into finer dust. And this means that the brightness and clarity of Saturn's rings today are not the same as they would have been in the distant past, because continuous exposure to this dust environment slowly alters the rings from the outside in. As spacecraft observations have shown, the outer regions of Saturn's rings are especially exposed to this process because they are less dense and more open to incoming material from space, while inner regions are somewhat shielded by higher particle density. But even there, micrometeoroid impacts continue to occur, and over time they contribute to a slow redistribution of material across the ring system, where larger fragments are gradually broken down, and smaller particles are either absorbed into Saturn or spread out into wider orbits, depending on local conditions. This process also interacts with Saturn's magnetic field, because when high-speed impacts create fine dust particles, those particles can become electrically charged through collisions and sunlight exposure. And once charged, they can respond to magnetic forces, meaning that micrometeoroid bombardment does not only reshape the rings mechanically, but also feeds into electromagnetic processes that can move material along magnetic field lines, connecting this erosion process directly to ring rain and atmospheric loss, creating a linked system of material transfer and destruction. Over long periods, this continuous erosion means that Saturn's rings are not just changing shape, but also losing mass, because every impact either removes material from stable orbits or converts it into smaller particles that are more likely to leave the ring system entirely. And when scientists model this over millions of years, the conclusion is that without a strong source of replenishment, the rings would slowly fade, become darker, and spread thinner, eventually losing the bright and structured appearance we see today, which suggests that the current ring system is part of a temporary phase in Saturn's history rather than a permanent feature. Titan, a moon with a dense atmosphere. Titan is one of the most unusual objects in the solar system because it is the only moon with a thick, Earth-like atmosphere. And when spacecraft like Cassini and the Huygens probe studied it closely, they revealed a world completely hidden under a dense orange haze where the surface cannot be seen directly from space, because the atmosphere is so thick and chemically active that it blocks visible light, creating a constant layer of haze made from complex organic compounds produced by sunlight interacting with methane and nitrogen high in the atmosphere. This atmosphere is mostly nitrogen, making it thicker than Earth's in terms of surface pressure, and this alone makes Titan stand out among moons, because it means that standing on its surface would feel like being deep underwater on Earth, not because of liquid water, but because of the weight of the air itself pressing down. And within this atmosphere, methane plays a key role, existing in multiple states across the moon's climate system, forming clouds, rain, rivers, and lakes that cycle through the surface in a way that is similar in structure to Earth's water cycle, but built from completely different chemistry under extremely cold conditions. When Cassini radar instruments were able to see through the thick haze, they revealed large methane lakes and seas near Titan's polar regions, especially in the north, where vast bodies of liquid hydrocarbons fill basins and valleys, creating a surface that is shaped not by water erosion, but by liquid methane and ethane flow. And these lakes are stable features over time, meaning that Titan has an active liquid cycle that shapes its surface, even though temperatures are so low that water behaves like rock and methane behaves like water. What makes Titan especially important is the chemistry happening in its upper atmosphere, where sunlight breaks apart methane molecules and allows them to recombine into more complex hydrocarbons and organic compounds, creating a constant production of chemical haze that slowly rains down onto the surface, adding layers of organic material over time. And this process is continuous, meaning Titan's surface is being modified by atmospheric chemistry on a global scale, even though no liquid water exists on the surface today. The surface itself, as revealed by radar mapping and Huygens descent, shows a mix of icy plains, dunes made from organic particles, and channels carved by flowing methane, showing that Titan has a full weather and erosion system, but one built on a completely different chemical foundation than Earth, where methane replaces water and ice replaces rock in defining how the surface changes over time, creating landscapes that are shaped by cold chemistry and slow atmospheric cycles rather than heat-driven geology. Titan's atmosphere also interacts with Saturn's magnetic field, because although it does not have a strong intrinsic magnetic field of its own, it exists within Saturn's magnetosphere, meaning that charged particles from the surrounding space environment can interact with its upper atmosphere, influencing chemistry and energy balance. And this adds another layer of complexity to Titan's atmospheric system, where internal chemistry, driven by sunlight and external energy from Saturn's magnetic environment, both contribute to its behavior. Over time, Titan stands out as one of the most Earth-like yet fundamentally different worlds in the Saturn system, because it combines a thick atmosphere, active weather cycles, stable surface liquids, and complex organic chemistry, but all under conditions so cold that water is frozen solid and behaves like bedrock, making it a world where familiar processes exist in unfamiliar forms, and where the same physical principles that shape Earth's climate and geology are operating under entirely different materials and temperatures, creating a system that is both recognizable in structure and completely alien in detail. Enceladus, ice plumes and subsurface ocean. Enceladus is one of the most important discoveries in the Saturn system because it completely changed the idea of what a small icy moon can be. And what Cassini revealed there was not a frozen, inactive body, but a world that is actively venting material into space through powerful jets of water vapor and ice particles that erupt from fractures near its south polar region. And these plumes are not weak or occasional emissions. They are continuous geysers that shoot material hundreds of kilometers above the surface before it falls back down or escapes into space, forming a diffuse cloud around Saturn known as the E-ring, which is constantly being replenished by Enceladus itself, meaning this small moon is directly feeding part of Saturn's ring system through active geological processes. The source of these plumes lies beneath the icy crust, where Cassini measurements of gravity and motion revealed strong evidence for a global subsurface ocean of liquid water hidden under the frozen surface. And this ocean is not a shallow pocket, but a large planet-wide layer of liquid trapped between the ice crust and a rocky core, kept in liquid form by tidal heating generated as Enceladus is stretched and compressed by Saturn's gravity during its orbit. And this constant flexing produces internal friction that generates heat, preventing the ocean from freezing completely, even at extreme distances from the Sun. As Cassini flew directly through the plume material, it detected water vapor, ice grains, salts, and organic molecules, showing that the subsurface ocean is not just liquid water, but a chemically active environment where complex compounds exist. And this discovery made Enceladus one of the most important targets in planetary science, because it shows that energy, liquid water, and organic chemistry can exist far from the Sun in environments completely hidden beneath icy crusts, and the plumes act as natural windows into this hidden ocean, allowing direct sampling of material from below the surface without landing on the Moon itself. The surface of Enceladus itself is bright and heavily reflective, covered in fresh ice that is constantly resurfaced by falling plume material, meaning the surface we see today is not ancient or heavily cratered, but geologically young in many regions, with smooth plains and fractured terrain near the South Pole where the tiger stripe fractures feed the plumes. And these long parallel cracks are the main vents for material escaping from the interior, showing that the surface is under continuous stress from internal ocean movement and tidal forces. Iapetus, the two-faced moon. Iapetus stands out in the Saturn system because of one of the most extreme and strange surface contrasts ever observed on a planetary body, where one hemisphere is dark and heavily coated with material while the other hemisphere is bright and icy, creating a clear division that makes the moon look almost split into two different worlds. And this sharp contrast is not gradual or subtle. It is one of the strongest albedo differences in the solar system, where one side reflects very little sunlight and appears almost black, while the opposite side reflects strongly and appears bright white, giving Iapetus its well-known two-faced appearance. This difference is linked to a combination of external material deposition and thermal effects, where the leading hemisphere of Iapetus, the side that faces forward in its orbit, collects dark dust and particles likely originating from other moons or outer ring material. And once this darker coating begins to form, it absorbs more sunlight, causing local heating that leads to sublimation of surface ice, which then redeposits on the brighter trailing side, reinforcing the contrast and making the dark regions even darker over time, while the bright regions remain relatively clean and icy, creating a feedback process that strengthens the divide between both hemispheres. Another major feature of Iapetus is its enormous equatorial ridge, a mountain range that runs almost perfectly along the moon's equator and rises dramatically above the surrounding terrain, reaching heights that are large compared to the size of the moon itself. And this ridge is unusual because it is not a single continuous mountain range formed by tectonics, like on Earth, but a structured feature that may have formed through a combination of past rotational dynamics and material deposition, possibly when Iapetus rotated much faster in its early history, causing material to accumulate along the equator or through the collapse of a former ring system around the moon that settled into an equatorial line. The surface of Iapetus is heavily cratered in many regions, showing that it is geologically old and has not been resurfaced in recent times. And the contrast between the dark and bright regions also affects temperature distribution, because the dark side absorbs more heat while the bright side reflects sunlight, creating thermal differences that can influence surface processes over long periods, even if they are slow compared to more active moons like Enceladus. Hyperion, the chaotic spinning moon. Hyperion is one of the strangest objects orbiting Saturn because it does not behave like a normal moon with a stable rotation. Instead, it spins in a chaotic and unpredictable way, tumbling through space rather than rotating smoothly around a fixed axis. And this chaotic rotation is caused by its highly irregular shape and weak gravitational binding, which makes it extremely sensitive to gravitational tugs from Saturn and nearby moons, causing its orientation in space to change in a way that is difficult to predict over long periods. Unlike larger spherical moons that have enough gravity to pull themselves into stable shapes, Hyperion is irregular and sponge-like, with a surface full of deep craters and low-density structure, meaning it does not have enough internal strength or mass to settle into a stable rotation pattern. And as a result, it behaves more like a drifting object caught in multiple gravitational influences at once, leading to a rotation that is chaotic rather than periodic. One of the most striking features of Hyperion is its porous surface, which gives it a sponge-like appearance, with large craters that appear to be filled with dark material. And this structure suggests a very low density interior, meaning that Hyperion is not a solid compact body, but a loosely held collection of material with significant empty space inside, which contributes to its unstable rotation and irregular motion through Saturn's gravitational field. Orbital dynamics, a crowded gravitational system. Saturn is not a simple planet, with a few moons moving quietly around it. It is a dense gravitational system where dozens of moons, ring particles, and embedded moonlets all interact at the same time, creating a constantly shifting environment where orbits are shaped, disturbed, and refined by repeated gravitational encounters. And the key idea is that nothing in this system moves in isolation, because every object is influenced by Saturn's gravity, but also by the gravity of nearby moons, and even by the collective mass of the rings themselves, which means that orbital paths are not fixed lines, but evolving routes that slowly adjust over time as small forces build up across long periods. Within the ring system alone, particles are not only orbiting Saturn independently, they are also constantly colliding with each other at low relative speeds, which sounds harmless, but is enough to slowly redistribute energy and angular momentum across the disk. And over time, this creates wave patterns, gaps, and sharp edges that are maintained by gravitational resonance with nearby moons, especially small shepherd moons that orbit close to ring boundaries and repeatedly pull particles into organized structures, meaning that what looks like a smooth ring from a distance is actually a highly structured system of countless micro-interactions happening continuously across thousands of kilometers. The moons of Saturn add another layer of complexity, because larger moons like Titan, Rhea, and Dione do not just orbit passively, they actively influence the motion of smaller bodies through resonance effects, where orbital periods lock into stable ratios that can either stabilize or destabilize regions of space. And this creates long-term patterns where certain orbital zones become cleared of debris, while others become dense with material. And over time, this process reshapes the entire architecture of Saturn's system, not through sudden events, but through slow gravitational tuning that operates over millions of years. Some moons even exchange material directly with the rings, especially small icy bodies that orbit within or near ring structures, where impacts and gravitational interactions can either remove particles from the rings or supply new material, creating a feedback loop between moons and rings that keeps the system dynamically active. And this is especially visible in regions like the F ring, where narrow structures are constantly disturbed by nearby moonlets that pass through or near the ring, creating braiding patterns and temporary clumps that form and dissolve as gravitational forces shift their positions. Over long timescales, these interactions create orbital migration, where moons slowly shift their positions due to tidal forces, because Saturn's gravity raises tides within the moons themselves, and energy is exchanged between rotational motion and orbital motion, causing some moons to gradually move outward, while others are locked into stable orbits. And this slow migration changes the spacing and resonance structure of the entire system, meaning that Saturn, today, is not in the same configuration it was millions of years ago, and it will not remain the same in the future. Even the rings are part of this long-term evolution because they are not permanent structures, but dynamically evolving disks that slowly lose mass through processes like ring rain and micrometeoroid erosion, while also being reshaped by gravitational resonances with moons. And this means that the ring system is gradually changing in both structure and mass distribution, with inner regions being more strongly affected by Saturn's magnetic field and atmospheric drag, and outer regions being more influenced by moon interactions and external impacts. Long-term evolution. Saturn's system is changing. Over millions of years, Saturn's system is not stable in a fixed configuration, but is slowly evolving through a combination of ring loss, moon migration, and gravitational reshaping. And the most important idea is that this system is not frozen in time, but is actively changing even if the changes are too slow to observe directly within a human lifetime. Because every orbit, every collision, and every tidal interaction contributes to a gradual redistribution of energy and material across the entire system. One of the clearest signs of long-term evolution is the gradual decay of the ring system, where material is being lost through multiple pathways, including ring rain into Saturn's atmosphere, micrometeoroid erosion from external dust impacts, and gravitational scattering by moons. And when these processes are combined, they suggest that the rings are not permanent structures, but are slowly being depleted over time, meaning that the bright and structured ring system seen today is part of a temporary phase in Saturn's history rather than a stable final state. At the same time, moons are not fixed in place either, because tidal interactions with Saturn transfer energy between the planet and its satellites, causing orbital migration where some moons slowly move outward over long timescales, while others remain in stable, resonant orbits. And this movement changes the spacing between moons, which in turn alters resonance patterns in the rings, meaning that the structure of the entire system is linked through a long chain of gravitational relationships that evolve together rather than separately. There is also evidence that some parts of the system may have formed or been reshaped relatively recently in geological terms, especially the ring system, which may have originated from the breakup of a larger icy body or moon that was torn apart by Saturn's gravity. And if this is correct, it means that the current ring structure is not an ancient feature, but a relatively recent addition to the Saturnian system, and it will continue to evolve as material is gradually lost or redistributed. Over very long timescales, the balance between ring formation and ring loss determines the future appearance of Saturn, because if loss processes dominate, the rings will gradually thin out and fade. While if new material is introduced through moon collisions or other events, the system can be partially replenished. But current evidence suggests that loss processes are dominant, meaning that the ring system is likely slowly moving toward a less massive and less visible state over time. Why Saturn feels scary in scientific terms. In scientific terms, Saturn is considered one of the most dynamically intense environments in the solar system, not because of emotion or interpretation, but because multiple extreme physical systems operate there at the same time, creating a layered environment where radiation, atmospheric motion, ring instability, and gravitational complexity all interact continuously, producing conditions that are difficult to model and constantly changing across different scales. The first major factor is radiation, because Saturn's magnetosphere traps high-energy particles in large radiation belts that extend around the planet, creating regions where spacecraft must carefully avoid or limit exposure. And these belts are not static. They shift and vary depending on solar wind conditions and internal plasma dynamics, meaning that the space environment around Saturn is always active and unpredictable at fine scales. The second factor is atmospheric dynamics, where wind speeds exceed 1,800 kilometers per hour and form stable banded jet streams driven by internal heat rather than sunlight alone, creating a system where deep energy flow continuously powers storms, lightning, and large-scale circulation patterns that extend across the planet. And this atmosphere is not calm or layered in a simple way, but is structured through fast-moving flows that interact across multiple depths. The third factor is ring instability, where the ring system is not a permanent structure, but a dynamic disk of particles constantly being reshaped by collisions, gravitational resonances, micrometeoroid erosion, and magnetic interactions, meaning that what appears stable is actually slowly changing, with material being redistributed, lost, and reorganized across long timescales. The fourth factor is gravitational complexity, because Saturn's dozens of moons interact through resonances, orbital migration, and material exchange with the rings, creating a crowded system where small gravitational changes can produce long-term shifts in orbital structure, and this makes the entire system sensitive to small variations that accumulate over time, producing a network of evolving relationships rather than fixed orbits.